Swayam Prabha. Digital India. Educated India.
So then we consider now a next example of a belt drive with and without no flexible belt. Okay, so this is again a system wherein, like, you know that okay, this is theta m here and this is theta l here. So this part of this derivation without flexible belt we have seen in the previous class, or we have seen previously. One can see from there the kinetic energy already we had expressed there. You again here also I would like you to kind of derive this in now this Lagrange formulation kind of a setting. So potential energy in this case is 0, okay, without flexible belt. Okay, so without belt your potential energy is 0, and under that case if you apply your equation with the equivalent inertia. See now the when you use a generalized coordinate as theta m here, okay, the motion of the motor side theta m, that is my generalized coordinate. If I define in that way, then I express my kinetic energy in terms of generalized coordinate, and then I get, like, this J equivalent naturally as a part of kinetic energy. So half J equivalent, which is equal to Jm plus Jl by n square, that times, like, theta m dot square, that will give me the kinetic energy expression, and this is now J equivalent. So this J equivalent will naturally come, and then when you apply Lagrange formulation for this case, you'll find the equation of motion coming up in terms of this J equivalent and things like that. And B equivalent, for example, here we'll consider as an external force, or we have to consider from the similar kind of a energy principle that we saw in the last class. Okay, previously what we have seen for the damping term, we introduced that as a external force. So now the question is, like, how do you deal with this system when there is a belt which is flexible, which is to be considered flexible? So what we do is, like, there is instead of, like, this kind of a rigid connection, we say that okay, there is a flexibility here. Okay, this part we have discussed a little bit in the last previous part also. So then when there is a flexibility or there is a spring here, okay, then whatever force that is getting applied to the belt by the motor will result in the tensioning of this or extension of this spring. Okay, and that's how, like, the theta for the load will no more be connected with theta for motor directly. Okay, it is not like theta m upon n will give you theta l. That is not possible now. Okay, so these become like independent degrees of freedom. Now if they are independent degrees of freedom, say theta m is given, theta l is given as an independent degree of freedom, then okay, the question is, can we find what is a extension in the spring? Okay, so that will be, we'll be able to find the extension in the spring, and once we have that extension in the spring, we can express that as say delta as an extension in the spring, and half k delta square will be our potential energy. Okay, so this is the additional part that we'll have, like we'll have previous kinetic energies and this additional potential energy of a belt that is to be considered now, and then we can use Lagrange formulation and derive the equations. So this part you can do as a part of your work here. We can move on from here now. So you carry out this derivation and see what is the equation of motion that you get, and one can interpret, and once you get the equation of motion, one can interpret them in terms of Newtonian kind of formulation way. Are these looking at the appropriate terms here that are to become coming in the final equation. Okay, that exercise you can do. So this becomes like a under actuated system. Okay, it has only one actuation for the motor, but 2 degrees of freedom motor and the load. So we'll see how these kind of systems can be dealt for the control. Now we can further extend it for the other case, okay, which is again another kind of a interesting problem. So you have a gear attached to the motor shaft, and to that output of the gear you have a link attached. Okay, this is typically, this will be a configuration for robotic systems. You have a motor and gear, and then further you have some links coming up there. You may have multiple links for the robot, of course, but we are considering now this is the most simplest kind of a form for robotic manipulator. Okay, so the kinetic energy for this system can be written in terms of inertia of the motor side. Okay, so this is Jm theta m dot square, and then you have an inertia of load coming up here, which is now hinged here. So the inertia of this link that will be coming up as transferred to the hub, that will come up as a kinetic energy. One can write this expression of kinetic energy in terms of this load inertia, or one can say, okay, I'll see this as a rigid body, and for this rigid body the center of mass is here. For the center of mass into velocity square, half of that will be the translational kinetic energy, and then I consider rotational kinetic energy, and then whatever that total I get in terms of theta L now alone, you have to express the translational kinetic energy of this rigid link also in terms of theta L, and then we can get this equivalent, okay, this J about this point. Okay, so one can directly consider that, or one can see it in terms of your translation kinetic energy and rotation kinetic energy separately. And then once you get this kinetic energy expression, you use the connection between theta m and theta L. So gearbox ratio will be the connection to express it only in one generalized coordinate theta m here. Okay, so this is typically an important step in Lagrangian formation, to see that the kinetic energy is expressed only in generalized coordinates. Okay, so in this case, if it has only 1 degree of freedom system, you need to have only one generalized coordinate to be there in the kinetic energy. Whatever you choose, it can be theta L also. There is no that theta L also can be generalized coordinate is also a possibility here. So we have chosen this theta m to express here. Okay, now if you see the potential energy of a system is mgl 1 minus cosine theta L. So this can again be expressed, this is okay, there is this L is little different from this L, because if you take a center of mass here, the potential energy for that, this should be for the center of mass here. Okay, so you make that correction. So this potential energy is in terms of theta L, but we need to convert it into in terms of theta m again, so as to have consistency in the generalized coordinate. Okay, so you define generalized coordinate as theta m, and then everything should be in consistency with that okay, all your kinetic energy and potential energy should be expressed in terms of this generalized coordinate. Okay, so that is a main kind of thing that maybe you may miss. Okay, so you need to make sure that okay, all the time the generalized coordinate, the energy expression should be in terms of generalized coordinate. Okay, so you do this Lagrangian formulation, and then you come back. I think you first do this formulation yourself and see that okay, what is the expression. So you define Lagrangian to be kinetic minus potential energy, and then apply this equation what we saw here. So this equation, if you apply, you should be able to get the equation of motion for this case as well. Okay. So do this exercise. This is important that once you do, you'll understand how things work. Okay, or some places you might kind of miss out some things that will get corrected. Okay, and next time when you do, you will not make those kind of mistakes. Okay, so with that you'll get this Lagrangian formulation, theta L replaced by theta m upon n, you get this kind of a equation of motion. Okay, and for this tau is like your torque applied in the direction of generalized coordinate theta m. So this is like directly a motor torque here. So this is motor torque, or there are other torques that might be coming in. So say for example, if you want to integrate this now with the motor equation, how will you do that? Think about that. Okay, so there'll be friction torques, and then there will be other torques that are coming. So see, we have already incorporated accounted for the motor inertia here. Okay, Jm is already considered here. So considering all these, one can see this torque can be consisting of missing torques that are not considered. So this inertia torque is considered. For example, damping is not considered here. So those are kind of things that one can think about to incorporate into these external forces in the direction of motor generalized coordinate, okay, or in the direction of theta m. Okay, so those kind of forces will come, incorporate that, and then you may be able to get the complete equation. And this can be integrated with for example with our motor equations. Okay, so motor equations we have derived in the previous classes, so that can be integrated with this equation to get appropriately the entire dynamics. So I'll leave this exercise for you to do. You can see that in the absence of this torque, okay, there is no torque that is applied by the motor. So this term will be 0 here. When this term is 0, you can see clearly that this basically becomes and also there is no friction. I mean, this torque consists of all this friction and other forces. Those all the forces are 0. Okay, then this gives you the equation of a pendulum only, right? So say if you don't have even a gearbox, then it will be simply Jm theta m double dot plus mgl upon n sine theta m upon n here, which is now this n is 1. There is no gearbox, so these are 1 quantities, and then so this is Jm plus Jl. It will become, sorry, it will not be, this will not be 0, but this will be 1 here. Gearbox is not there, means you have a direct transmission, so there is n is equal to 1. So then this falls into reduces to equation of a pendulum without gearbox. With gearbox, you can see this n coming up here, and things like that. Like that, one can have this physical interpretation of final equation formed, okay, and say that okay, this makes sense. Okay, so now this can be further developed by incorporating these other terms also into this equation, this damping term especially, and you can additionally have the Coulomb and other kind of a friction models that can be incorporated. Okay, so that I'll leave to you to look at. Then we can see this other application, which is dynamics of this 2R manipulator. Okay, so that is so I would suggest here again you can take this kind of a configuration, pause here, and think of your fundamentals from kinematics and dynamics, and determine what are the energies here. okay, kinetic energy and potential energy. So kinetic energy, for that you need a center of mass of these linkages, and at that point you need a translation and rotational kinetic energy. Okay, so translational kinetic energy from the center of mass velocity, and rotational kinetic energy from the rigid body omega, angular velocity of that particular rigid body. Notice here that this theta 2 is measured in the coordinate frame which is moving here. So while writing energies, you need to account for that and write proper expressions, because this is not this theta 2 is not defined with respect to the stationary x axis. Okay, so stationary, with respect to stationary x axis, the the angle will be theta 1 plus theta 2, okay, for this link. Okay, this is done because, like, theta 2 is deformation, or like is not deformation, is the angle of rotation of the motor that is existing at this point. Okay, so if you have a robot which is, like, having these multiple motors attached to its different joints, then we typically need final dynamics in terms of the joint motions, rather than, like, these otherwise we'll have to find out the joint motion from the other coordinates. If I define theta 2 differently, I'll have to find out what is the joint motion. Okay, so at this point, let's you just pause and, like, derive the equations for velocity first. Okay, so we just need velocity. We don't need acceleration analysis here. We just need a velocity analysis here, and get the expressions for total velocity and further kinetic energy in terms of those velocities. Okay, so velocities of the center of masses of these two linkages is what we need to get from our kinematics. So how do you go about that? You can write the coordinates of x and y coordinates of this CG point here. Okay, given all the geometry parameters, and same thing you can do for the CG point here for second link. What are the coordinates x and y for the CG point for the second link, and based on those coordinates, once you get the coordinates, you get, say, x CG2 and y CG2. Then you differentiate that to get x dot CG2 and y dot CG2, and your total velocity of CG will be square root of x square plus y square, x dot CG2 square plus y dot CG2 square. Okay, so that's how one can get total velocity, and once you get that velocity or velocity square, you can use that in the expression of kinetic energy for writing kinetic energy of this. So please do this derivation yourself, and then you can proceed to look at the further further developments that we are discussing. Okay, so I'll pause here and discuss this further in the next part of the lecture. Okay, so now we'll continue with our topic of discussion of Lagrange formulation with this 2R manipulator, and then we'll continue further about some of the properties, very interesting properties that these mechanical systems yield with the Lagrange formulation. Okay, so let us see the screen. Let me get the pointer now, right? So for this formulation, I had asked you to do in the as a part of your own activity. I hope you would have done that. Please see that you have done yourself before getting into, like, seeing the further thing, because that will kind of give you the real feel of what is happening, and also any mistakes you have kind of made along the path, they'll get kind of rectified, and that will kind of open up some concepts. Please do that activity before we move on. So now, for such a manipulator, you can use your kinematics fundamentals and get to these equations for the velocity. Okay, for example, the velocity of the CG C1 VC1 is given here in terms of the coordinate q1 here. Okay, so this is a Jacobian. Okay, this is a new concept called Jacobian, which expresses velocities of interest. Okay, this velocity is c1 in terms of the velocities of generalized coordinates. Okay, so this generalized coordinate q here, so q1 and q2 are generalized coordinates, so q1 and q2 dots will be formed by this vector, and this matrix, when it's multiplied by that, you will see this velocity getting represented in this kind of form. If you just work out it based on using our kinematics and dynamics fundamentals, then also you can see the same thing. Let me get to that. So if you see here, these are the equations that you will start writing, and you can see this is q1 here and q2 here. Based on that, you can write the coordinates of the CGs of the links x1 and x1 y1 and x2 y2 for link 1 and 2, and you are seeing here there are the coordinates written here, and x2 y2 are written over here, x2 and y2, and then further differentiation of that will give you x2 dot y2 dot and x1 dot y1 dot, and you just take out this q1 dot out of these, q1 dot out of these, and q2 dot is not there in the x1 case, so that those terms will be 0, and you can form this Jacobian matrix as we have seen in the last part. Okay, so this part. Okay, so that's how you get this the velocities in terms of a Jacobian matrix, and this Jacobian has some value. We'll see what value it adds, especially for the robotic systems. It has significance when the Jacobian becomes singular matrix, then you'll have a problem in operating that robot. Okay, so maybe that much is now enough for the discussion of Jacobian. But this is an interesting way of concept and write the equations of velocities of linkages, especially there are CGs here for the sake of writing kinetic energies. So that's how you then develop the kinetic energy, and by in the Jacobian form, and further you get a rotational form added to it, and then this rotational form becomes based on the angular velocities of linkages, link 1 and link 2. You add that, and here they are kind of added in some kind of a form which can be matrix multiplication representation here. So this rotational kinetic energy, I mean, you can see that this is same as what this expression gives you. Okay, so it's just written in the by considering these q1 and q2s in this kind of a form. So this may be useful for some cases when you kind of start developing things for more complicated systems. Then potential energy of the system is straightforward. You can write based on the relative CG locations and mass multiplied by the length and the location, and by the gravity. Okay, and you get this potential energy of the system, and then you crank in the Lagrange equations. You do it by yourself. I'll show you some part of the derivation here. You can pause and look at it if at all, if you have to cross check your own derived stuff. You can do it in this fashion here. So look here, we have written expression for kinetic energy, now not in the Jacobian form, but complete expressions as you get, and then they are simplified here, Vc1 square, Vc2 square. There is some simplification that happens there, and then further you go and you develop this complete form of kinetic energy here, and start now collecting some terms to kind of express this kinetic energy in the form something times q1 dot square only. Okay, then something times q1 dot q2 dot terms here. So these are we are kind of generating some kind of a quadratic form for the kinetic energy expression here. Okay, so this has also a value. One has to kind of see that. We'll see we'll discuss what is this value that we add by using this kind of a form. Okay, so one can write in kinetic energy directly, not directly, I mean by simplification, one can write the kinetic energy in terms of this vector here, and then like this matrix multiplication, and again this other vector here. Okay, the vector is of the velocities, the joint velocities. So these are the velocity, this is the total kinetic energy of the system expressed in the form of a generalized coordinate velocities. And in general, these internal terms are functions of q1, q2, and so forth. They are not functions of q1 dot and q2 dots. Okay, this is to be point to be noted. Once you get this kind of a kinetic energy expression, then you further start developing the Lagrange formulation. You write the expression for potential energy here, and then express the Lagrange and by kinetic energy minus potential energy, and further you start differentiating, and this differentiation gives you different terms in the expression. Okay. So while differentiating, if you are expressing in terms of like these d11 coefficients here, we need to make sure that these coefficients are further functions of there may be further functions of q. Okay, so wherever this full differentiation may come, like this term need to be considered accordingly. So say for example, this d11 term has this cosine q2 part inside it. So when you are differentiating in with respect to time, then your additional part of the terms will be coming there. Okay, so this is like you can see here, d11 dot terms is coming here. Okay, and you can account for that accordingly. So like that you keep on doing this formulation and simplification of algebraic simplification of the terms, considering all different derivatives that exist in Lagrange formulation, and then you can, for q1 part, you get this particular equation for q1 alone, variable q1. Then you get another equation for q2 part by considering the differentiation or generalized coordinate q2 for Lagrange equation, and then you get this second part of equation q2. Okay, then you assemble these equations in certain kind of a form. Okay, and why we do that, we'll see it later. But the form is basically you consider this matrix dq to be having this kind of a form, then cq q dot to be having some form here. Okay, and then these gq terms are basically gravity terms coming because of the gravity forces in the potential energy, and you have a torque vector here. And with this expression, your complete Lagrangian equation will get developed. Okay, so this will get developed in the matrix form. Okay, so we'll further see what are the properties of these matrices a little later, but you are expressing this particularly in these forms for some reason here. Okay, and we'll see that reason in a while. Okay, so this is the formulation of 2R manipulator that we have seen here, and the same thing is put up here. Now with this formulation, we further move on to see some of the interesting properties of this Lagrange formulation. Okay, so the equations are expressed in this form, and as you have seen, these d11 d12 terms are defined as here also, and in the other longhand derivation also, and these are the c terms mentioned here, and with this you have these complete equations of dynamics of a manipulator derived. Now if you notice here, this d11 d12 d21 and d22, they form some kind of a matrix multiplying q1 double dot q2 double dot in the matrix equation form. So this is a D matrix here, and then this C matrix we define out of these terms here, okay, which are basically not having any double derivatives terms, okay, and we are not considering damping in the system, no loss of the energy in the system, and then there are these gravity terms that are coming here. Okay, so with this there is a very interesting property called skew symmetry property of d dot minus 2c matrix, which will come, which you can verify that or validate that property. But for this D matrix itself, like you have this property coming up here, that this D matrix is a symmetric matrix, and it is positive definite matrix. Okay, so this is an invertible D matrix that will come here. So we will look at this little more detail as a generalized thing, but you need to notice that this D matrix is coming out of the energy expression. Okay, so one can, without even Lagrange formulation, one can write this D matrix as once you write the kinetic energy of the system in the form that was expressed in the equations here. You can see this form of equation of kinetic energy was written in this form. Okay, so D11, like this was a D0 term here, which can be split into two parts, like one part can be written here, other part can be written here, which will be both same parts. Okay, so this D0 by 2 we can become actually. So this form of the expression, these terms directly appear in the expression of the Lagrange formulated equations of motion. So that is what is important thing to notice here, and one can understand very easily why they would come once you have this energy expressed in this particular kind of a form. Okay, so maybe we will stop here for now, and we will continue the discussion of this generalized form of this rigid body equation in the next part of this lecture. Okay, so you go ahead and make sure that you understand this application to 2-hour manipulator, so that this generalization can be understood in a relatively easy way. So that's what I would suggest you to do, and we will stop for now here. Okay.